This topic is covered very fast with the expectation that the video viewer can start, stop, fast forward, rewind, pause, etc. at their leisure. The two-thirds solution, rolling uphill with and without friction. Here's an interesting three-part problem that illustrates the implications of rolling inertial moment and tells the story of a family of two-thirds fractions. Our problem statement is that a solid cylinder of mass m and radius r is given an initial speed v toward a fixed inclined plane of angle theta. The coefficient of kinetic and static friction between the plane and the cylinder are mu k and mu s respectively. The angle theta is sufficiently small that the cylinder rolls up the plane without slipping. First task is to calculate the acceleration of the cylinder. Now we presume that the cylinder will slow to a stop as it rolls up the incline, so this is actually a deceleration. First, a question for the class. Which of these items contribute directly to the deceleration of the rolling cylinder on the incline? We've got mass, the fact that it's a solid cylinder, the radius, the angle, the friction coefficients, the rolling without slipping, and later on we'll talk about it being frictionless. Let's think about that for a bit. Talk amongst yourselves. Okay, did we figure this one out? What if I told you it was only these? The solid cylinder, the angle theta, and the fact that it's rolling without slipping. What? The mass and the radius don't matter? Correct. Let's see why. Working it out, we start with our givens, all the things that we were handed. Some of these we will need and some we don't. For the first part of the problem, we want to find the deceleration of the cylinder on the incline rolling without slipping. Here's a handful of equations that we've gathered from kinematics, dynamics, conservation of energy, friction, and such. Some of these we might be able to use. What are the names of these equations? Stay tuned, I'll tell you. Let's start here with this equation, a kinematic equation I'm calling final velocity from distance accelerated. When I solve this for acceleration, we see that acceleration is just equal to the negative v squared divided by 2d. Wait, that seems too easy. That's almost the answer. Not quite. We still need to find the diagonal distance traveled up the incline. Let's look for d from our definition of sine by finding y, which is going to come from our gravitational potential energy. We're probably going to need a few more tools, like angular to linear velocity conversion, conservation of energy, components of energy, the definition of translational kinetic energy, the definition of rotational kinetic energy, and the inertial moment, and of course the inertial moment coefficient for solid cylinders. An illustration is nice too. At the bottom of the incline, the only energy that's there is just the kinetic energies. So we have our linear kinetic energy and our rotational kinetic energy. If I factor out the 1/2 and clean this up a little bit, substitute in the inertia and v over r for omega, factor out our m, clean out the r's, factor out the v squareds, clean up our fraction a little bit more, and now we have E1, the total initial energy at the bottom of the incline. I'm going to stash that up there at the top. When the cylinder comes to a stop on the incline at the top, the only energy left is our gravitational potential energy, so that makes that really easy to find. If I set these two equal to each other for energy conservation, I can actually factor out m and solve this for y, the vertical distance that we traveled from the bottom to the top of the incline. We're almost there. Finally, we're going to use y to find d. We had this equation, but now I can set it equal to that one and use that to solve for d. This is the diagonal distance that we're traveling up the incline. And remember, all I needed was d for my equation. So put d back into the original acceleration equation. Get rid of those v squares. And then we get our final answer for part A, the deceleration, as the cylinder rolls up the hill. Yes, it had no mass or velocity in there at all. It seems that mass and velocity of the cylinder don't actually matter. And by the way, look, it's our first 2/3. Why 2/3? Because inertia equals kmr squared, where k is a coefficient that's distinct for different shapes. For solid cylinders, k equals 1/2, so I equals 1/2 mr squared. And k is also the ratio of rotational kinetic energy to translational kinetic energy for things that are rolling without slipping. When I put this into the energy equation, I see that there's a 2-to-1 ratio in our kinetic energies for a total of 3. If I normalize that by dividing everything by 3, I see that translational kinetic energy is 2/3 of the total. Yeah, it's incredible. So what does this look like? I've got a little animation here. Look in the upper right hand corner and see how the kinetic energies immediately transition over to the gravitational potential energy. Let me run that again and take a look at the gear teeth engaging. What direction does the roller and the track push against each other with? So we have the same problem statement, but this time we're asked to calculate the frictional force on the cylinder when it's on the incline. So what is the direction of the friction on a cylinder rolling without slipping? Well, we just saw an example of that with the little gear teeth, but I'm talking about when something is smooth but still rolling without slipping. A lot of people think that maybe the frictional force on the roller is in the same direction as the velocity. Some people think that the frictional force on the roller is in the opposite direction, thinking about it in terms of a torque or something like that. Talk amongst yourselves. So what did we decide? Well, what if I told you that this was the correct answer, that the force of friction is in the same direction as the velocity? Now, I have to throw in a disclaimer here. Before we get too far into rolling and friction, we have to acknowledge that this is an idealized problem. And the mythical idealized universe, static friction can't really do work or counter motion efforts on something rolling. We know that static friction must be there to roll, but the values derived here are only an imperfect model of reality. If we take a look at normal force and friction models when something is moving, we see that the roller must push backwards on the ground to move forward. Therefore, the ground always pushes forward on the roller. So we're only interested in the forces on the rolling cylinder, and that force is in the same direction as the velocity. In the real world, rolling things deform and make contact over an area, not just one point, and the friction does resist everything. It sort of looks something like this. So let's work it out in its idealized way. Here are our givens again. For the second part of this problem, we're going to build a sum of forces equation. So there's that. We have the sum of forces equal to the weight and the normal force and the friction, and they all add together to produce an acceleration. Force vector diagram would be helpful also. Notice here that I've put the force as coming from the center of the roller, even though it would be applied at the contact point. I do this for geometric simplicity. First, let's examine forces that are perpendicular to the incline. These are only the normal force and the component of the weight that's perpendicular, and they seem to be canceling out. This solves for the normal force, but it's really not much help for us now. Let's take a look at forces that are parallel to the incline. This is the friction force and the parallel component of the weight that do contribute to the deceleration. If I solve for the friction force, I get that, which is mass times acceleration plus our parallel weight. And then I replace that with the weight times sine theta, and then replace weight with mass times g. I start to see something that starts to look familiar. I factor out the mass, and I'm almost done. Now, we know what A is from the previous part of the problem, so I can substitute that in there, like this. And I start to see something I can clean up a little. We factor out the g sine thetas, clean up the fractions, and we see that our frictional force is 1/3 mass times g times sine theta. This is 1/3 of the parallel component of weight. In the last portion of our problem, we're trying to find the acceleration of the object if the inclined plane is frictionless. So it's rolling without slipping up to the base of the incline, but once it gets on the incline, then there's no friction. So I can't say it's rolling up the plane without slipping. What does slipping look like? Well, it looks like that, except, we have a cylinder, not a goat. What do rolling things do when there is little or no friction? Well, let's think about that for a minute. Talk amongst yourselves. What'd you come up with? Well, here's a hint. Do we call that? What do we call that? Do we call it sliding? Do we call it skidding? I like skidding. I'm going to call it skidding. So what does that even mean? Well, it means that our rolling kinetic energy is the same throughout the entire situation. It's the same when it's on the flat part, and it's the same when it's on the incline. So let's work it out. Here's our initial givens, and we're going to try to find the deceleration of the cylinder rolling up the incline with no friction. We can do what we did before in part A with a few minor alterations. We still have a situation at the bottom of the incline where we only have kinetic energy, so that part hasn't changed much. But at the top, now we have gravitational potential and rotational kinetic energy. So when I put those in the equation, I get a slightly different answer for E2. I substitute in the inertia and the V over R as we did before. I factor out the m's, cancel out the r's, and I end up with an E2 that looks a little bit different than what we had before. This is the total final energy at the top stopping point. Remember last time all we had was mgy. Now let's substitute these into conservation of energy. This is what we did before, but now we have that new term for E2. We factor out the m, we collect like terms, we clean up the fractions, and now we have y for the slipping case. We can use that like we did before to find out what our diagonal distance traveled was. So now we have that diagonal distance, and we can substitute that d into the old acceleration equation, just like we did before. And we find out what our acceleration is for part C. Here's what this one looks like. I'm going to use little ball bearings to represent sliding. And you see how it doesn't get up quite so high, and it's slipping in place and skidding. Watch the distribution of energy in the top corner when I run this again. Okay, we have the same distribution, but now look, only the translational kinetic energy is converted to gravitational potential. The rotational stays put. So without that added energy, we can't go as high up the incline. So the way the energy is distributed differently in each case determines the ratio of things. So how does the acceleration in part A compare to the acceleration in part C? That is to say, the no slipping acceleration with the slipping acceleration. Well, when I do a ratio, I get a perfect 2/3. Yeah, that's amazing. Can you believe it? What if I compare the diagonal distances from part A to the diagonal distances in part C? Well, again, the ratio comes out to be 2/3. That's amazing. How does the vertical distance, which affects gravitational potential, for part A compare to part C? Well, we already know that it didn't get up as high the second time. So when we put this in the ratio, yep, sure enough, we get 2/3. That's astounding! Finally, and you sort of know this one already, how does our system's translational kinetic energy compare to the system's total energy? Well, when I work that one out, I get 2/3. 2/3. Again, all because of this little number right there, that coefficient. Yeah, it's crazy. We gotta stop this. This is out of control. Here's a final question for the class. What would the 2/3 solution have to be called if we used a solid sphere instead of a solid cylinder? That would make a great exam question.